Hi, welcome to this session of page replacement. Last class we had discussed about page faults and how it occurs. We know that when a processor needs to execute a particular page and the page is not available in memory, a page fault occurs. And also we had seen that access to a page marked invalid causes a page fault trap to the operating system. And when a page fault trap occurs, the operating system fetches whether the page is there in the backing store. If it is there in the backing store, it has to take that from there and place it in the physical memory, and it has to update the page in table. And this is known as a page replacement. When a page fault occurs, a page replacement is needed. Over allocation of memory is prevented by modifying the page fault service routine to replace the pages. And every operating system has its own replacement schemes. Whenever a page fault occurs, how page replacement is done is given through an approach, and in this approach we can see that when a page fault occurs, it finds the location of the desired page on the disk. If there is a free frame, then the page is uploaded there. Otherwise, what happens? So actually the situation is this: when we have a page fault, that is a reference to an invalid page is made, then it has to be checked in the backing store and it has to be replaced in the page has to be loaded in the main memory, and the table has to be updated accordingly. But when the physical memory has free frames, then it is okay. What happens when the physical memory has no free frames? In that case, it has to take one page from there and then to reload the faulted page. And this replacing page is called a victim page, and that victim is taken back to the backing store. So this approach may not be clear now. Now we will see the algorithms and then everything will be clear for you. That is how page replacement is done and how the victim page is chosen. And for this page replacement, we have many algorithms. We have three algorithms to see. The first one is a FIFO replacement algorithm. Then we have LRU replacement algorithm, and then we have an optimal page replacement algorithm. First we will see the FIFO replacement algorithm with a reference string of given reference string, and we are assuming that we have 3 frames, that is 3 pages can be loaded in memory per process. So these are the 3 frames, and we have the reference string of this type. So what is a reference string? A reference string is the string of memory reference, that is called a reference string. And when a page is brought into memory, we insert at the tail of the queue in this FIFO page replacement algorithm, first in, first out. So when a page may be replaced, the oldest page is chosen for the replacement. We will see how the algorithm works. So we have this reference string and we have 3 frames. So first page 7 has to be loaded in memory. It fetches there is no such page, so it has to be loaded. A page fault occurs, and then frame was free, there is no problem. And then the frame 0 has to be loaded. Again there is a page fault occurring, but the frame is free, so there is no problem. And then 1 is to be loaded. So free frame was there, so everything is loaded. So now what happens when 2 has to be fetched for the physical memory? A page fault occurs, and there is no free frame in the physical memory. So the algorithm has to choose a victim from the given list of 701. So in this particular scheme of the FIFO page replacement algorithm, how it chooses a victim? It chooses a victim. The victim is the first one in. So the first in was 7 and 7 is removed and 2 is replaced. So we can see that now it will be 201 in the physical memory. Then now we have next to reference is 0. 0 is already there in the memory, so there is no page fault. Next to be referenced is 3 and there is no space and 3 is not present there. So we need to find a victim. How we are going to choose the victim? That is based on the first in basis. So once 7 was removed, the next person in was 0 and so now we are removing 0 and 3 is replaced there. Now the next referencing string is 0. So we need to choose the victim. The victim is 1. A page fault is there and 1 is replaced with a 0. So next referencing is 4 and the victim will be the first in 2. 2 is replaced with 4. Next referencing is 2. So 2 is not present. Victim is 3 and it is replaced with 2. The next reference is 3. So 0 is replaced with 3. Next reference is 0 and 4 is the victim chosen and it is replaced with 0. And the situation goes on like this until we come to the last page of the reference string. So here we can see that the page fault is not minimum page. There is a large number of page faults, but this is a very simple scheme. And page fault is, we have the number of page fault as 3, 4, 5, 6, 7, 8, 9, 10, 12, 3, 15 is the page fault rate. So now we need to choose an algorithm with lesser page fault, and for that we are going for another algorithm known as the least recently used algorithm or LRU replacement algorithm. So the strategy of the least replacement algorithm is based on the most recent reference. That is, it is using the past knowledge. Least recently used one will be kept and the previous one will be replaced. And it is not needing a future knowledge and it is taking the past knowledge. We will see how the algorithm is working for the same reference string. Okay, so first we have 3 frames and 7, there is a page fault, 7 is placed, 0 is placed, a page fault is there, still there is no victim. There is space, enough space in the physical memory, and then 1 is placed, page fault is there but there is no victim as all the pages are, all the frames are now filled. Now next we need to fill 2. Next we are going to reference 2. Actually what happens now? What happens is it is checking the previous ones. Which one? Now we have 701. So which one to replace? The recently referenced ones were 0 and 1. So it is replacing 7 and 2 is placed there. Then next is fetching for 0. There is 0 is present, so there is no page fault and no replacement needed. And then next fetching is 3 and 3 is not present here. So we need a replacement. Then how it fetches? It fetches the recently used page. The recently used pages are 0, 2 and 1. So 0 and 2 are kept there and 1 is little far behind. So 1 is replaced with 3. So now I think this strategy is clear for you. Then next reference is 0. 0, no need for a page fault, it is already present. Next reference is 4. So how the victim is chosen? The victim is chosen based on the least recently used reference. Okay, how we have least. So here actually what happens is the least recently used pages 0 and 3 are kept and 2 is replaced with 4. And next time when 2 is referenced, what happens? The least recently used pages 0 and 4 are kept and 3 is replaced with 2. In the case of 3, what happens is the page with the lesser backward distance is kept, that is 2 and 4 are kept and 3 is replaced. So I think now the idea is clear for you. It goes on like this, and when 0 is referenced here in this list, the least recently used ones 2 and 1 are kept and 3 is replaced with a 0. When 1 is referenced, 1 is already there. There is no page fault, and it goes on till the last reference string. And we can see that in this scheme, the page fault rate is reduced. So now the page fault rate is 12. So in our earlier case, in the FIFO replacement algorithm, we had 15 as the page fault rate. Now it is 12. So it is reduced, and this is a better scheme. That is, it is better than FIFO as the page fault rate is reduced. And this algorithm is a good algorithm, and it is frequently used, and it always associates time of last use with each page, that is for finding the least recently used one. And this algorithm commonly has 2 implementations. One is the counter implementation and the other one is a stack implementation. In the counter implementation, what it does is every page is having a counter, and every time a page is referenced, copy the clock into the counter, and when a page needs to be changed, look at the counters for the minimum value, for the smallest value, that is for finding the least recently used ones, and whenever needed it is searched through the table also. And in the stack implementation, we have to keep a stack of page numbers in a doubly linked list format. And from these 2 algorithms, this LRU page replacement algorithm is better, which is having lesser number of page faults. The next algorithm in this category is optimal page replacement algorithm, and this algorithm is having the lowest page fault rate of all the algorithms. The strategy followed for this algorithm is it will be replacing pages that will not be used for the longest period of time. We will take the same reference string and we'll see how the algorithm is going to work. So we have 3 frames, and the first time a page fault occurs, but the memory was free, so there is no need of finding a victim or replacing some page. Then 0 is loaded, then 1 is loaded. So when we need to load the page 2, what happens is we need to find a victim. So the victim is found based on the future knowledge, which will not be used for the longest period of time. Out of 7, 0, 1, we can see that 0 is used in the recent future and 1 is used in the recent future. So 7 is far, so 7 is replaced with 2. 7 is victimized. Then 0 is referenced for the next time. 0 is present, so there is no page fault. Then when 3 is referenced, out of 2, 0, 1, which page to be victimized? 2 is used in the recent future. 0 will be used, so 1 can be victimized. So 1 is replaced with 3. Then when 0 is referenced, there is no page fault. 4 is referenced, which has to be replaced from 203. 2 will be used in the future. 3 will be used in the recent future. So 0 is far. So 0 is replaced with, or 0 is victimized and replaced with 4. Similarly, it goes on like this till the last reference string, last page. And we can see that the page fault rate is only 9. So in the FIFO case, it was 15. In LRU, it was 12, and now it's reduced to 9. So this is better than FIFO and LRU, but it is not used frequently because this is difficult to implement. This algorithm, as we had seen, is working on, it requires the future knowledge of the reference string, which is very difficult to extract. So it is very difficult to implement.